So let's work through some examples. Our first example is PCl3. We need to start with the best Lewis structure. So I'm going to add up my valence electrons, which is 5 for phosphorus and 7 for each of the chlorines. This gives me 26 electrons. Then phosphorus is my central atom. I've connected the 3 chlorines, put in lone pairs on the outside atoms. I still had 2 I could put on my phosphorus. And if you go through and calculate formal charges, everything has a 0 formal charge. So I'll have phosphorus with a lone pair, 3 chlorines connected. Each chlorine has 3 lone pairs. This is my best Lewis structure. Now, translating this into a VSEPR structure, I'm going to count the number of things around phosphorus. So we're only going to worry right now about the geometry around the central atom. So phosphorus has 4 things around it. It has 3 chlorines and 1 lone pair. So that's 4 things. Now the coordination number is 3 because it only has 3 atoms around it. But the positions of those atoms are also affected by the lone pair, right? So 4 things affecting my electron geometry. So I'm going to write phosphorus and then a geometry with a steric number of 4 that's based in tetrahedral. So I've just got like some placeholder spaces, like what is the shape going to look like around phosphorus? And then one of those positions is a lone pair. So I've got a red X through it because I am not going to draw a bond to a lone pair. I'm just going to put the lone pair on the atom, but then every other position, the angle at which I drew it, that's where the other atoms will be attached to show the shape. So I have phosphorus, then the rest of my trigonal pyramidal shape with the chlorines. I'm going to fill in my lone pair on phosphorus. I am also going to fill in my lone pairs on the chlorines. So with VSEPR geometries, I do want you to show all bonds, all lone pairs, all formal charges. Now, you will run into some situations where it feels really weird, like how am I supposed to show a double bond in perspective? We can talk about that because it is hard to do, but I want you to include everything. All lone pairs, all formal charges with the correct shape. So this is my final picture of the VSEPR geometry for PCl3. The next example is BRF3. So valence electrons, 7 from bromine, 7 from each fluorine. That's 28 electrons. Connect fluorine to bromine. Bromine's my central atom. And put lone pairs around the fluorines. I am left with 4 electrons that I still have to put in here. So I put them on bromine, and that's okay. So my bromine has more than 8 electrons around it, but it is in the 4th row of the periodic table. So I am allowed to expand its octet. Okay, so that's all my electrons. Calculate formal charges. That's 0 formal charge also. So that's nice and happy. 0 formal charge on my fluorines. I have 5 things connected to bromine. So I have 3 fluorines and 2 lone pairs. So that's 5 things total. This means that I have to worry about Bent's rule. So out of the lone pairs and the fluorines, I have to choose what goes axial and what goes equatorial. And lone pairs are large. And fluorine is small, right? It's the most electronegative atom. It's the smallest one we're going to deal with. So lone pairs in the equatorial positions, and my fluorines go axial. I mean, I have a 3rd fluorine, so I'm going to put that equatorial because I don't have anywhere else to put it. And my result is T-shaped. And this is what my VSEPR geometry looks like with approximated bond angles, right? They'd be squished a little bit, but they're based in 90 from each other. And I have all of my lone pairs in here, and there were no formal charges. All right, 3rd example with a formal charge, just to make sure that we've got something that includes that. Let's do IF4 minus. So 7 electrons from iodine, 7 electrons from each of the fluorines, plus 1 extra, because it's a negative charged molecule. So we have 36 electrons to put around this. Connect my 4 fluorines with single bonds, put lone pairs around all of my fluorines, and that gives me 8, 16, 24, that gives me 32 electrons. I still have 4 electrons to deal with, and I cannot put them on fluorine at all, right? Fluorine is in the second row. Each one of these has 8 electrons. I cannot expand its octet. I'm just going to stick them on the central atom. Iodine is like 5th row of the periodic table. It's big. It's in the area where we've said we can expand the octet. It's great. It's a big atom. It's not even a notice probably that those electrons are there other than the shape of the molecule. So what I have, and we're putting them on as lone pairs. So I have 4 atoms and 2 lone pairs. That's a steric number of 6. So 4 atoms, 2 lone pairs. My formal charges, fluorine has a 0 formal charge when you calculate it. The iodine has a negative formal charge. Now, okay, fine. It's not the more electronegative atom in this molecule, but we have minimized the formal charge. So you can try this out if you would like, but there's no way for us to get that negative charge onto the fluorine without completely disconnecting it from the iodine. So this is the best Lewis structure, the best I could do. I met the octet for everything. I minimized my formal charge. It's not perfect, but it really is the best that I could do. All right. So 6 things, but the coordination number is 4. So around iodine, I have my electron geometry that is octahedral. So six things around it. Put in a lone pair on any spot, and then the second lone pair is just going to go as far away from the first one as it can get. What this gives me is a square planar molecule. So I've got my 4 fluorines all in one plane, right, 90 degrees away from each other, and then the 2 lone pairs are as far apart from each other as they can get on the iodine, and the iodine has a negative formal charge. So this is my square planar IF4 minus, all of my lone pairs, all of my formal charges shown. So you should always include all lone pairs, all formal charges. If it's a double bond, draw it as a double bond. If it's a triple bond, draw it as a triple bond.